this video, we are going to look at velocity time graphs. So far in these videos, we've been looking at the Suva equations and we've been solving problems in one dimension, so motion in one dimension, using the Suva equations. In a few videos' time, we'll go back to the Suva equations and we'll use them to solve problems in two dimensions, so projectile motion, which is in two dimensions. But in the meantime, just for a couple videos, we're going to look at velocity time graphs, as these are quite common in kinematics and they can be very useful. So it's important to know how they work and how you can use them. So let's look at the following example. A car is moving in a straight line at 5 meters per second. After 3 seconds, it begins to accelerate at a rate of 1 meter per second in the direction of travel. It accelerates like this for 3 further seconds. Draw a velocity time graph of the motion and calculate the total distance traveled. So there's quite a lot of information there. It's quite wordy, but it's not so bad. Let's just start doing what they asked. So the first thing to do is draw a velocity time graph. All a velocity time graph is the velocity plotted against the time. So let's get up an axis. You'll always have a pair of axes that look like this. You always have time as the x-axis, and that's just generally true. It's a common convention. Whenever you're plotting time against something else, you plot time along the x-axis and the other thing along the y-axis. So the velocity is the y-axis in this case. Now I've not drawn actual numbers onto the axes, but I'm going to take one of these squares here to be 1 unit. So along the t-axis, as we go each square is a second. So between each of these lines is 1 second, and going up the v-axis is 1 meter per second. So that's the velocity, so it's in meters per second. So they're my units, and that's my scale, and I will start trying to answer this question. So at the beginning of the problem, when time is at 0, the car is already moving at 5 meters per second, and it continues to do this for 3 seconds. So we start by drawing a line that looks like this. So it's up at 5 on the v-axis and it goes along for 3 along the t-axis, because the car is driving at 5 meters per second for 3 seconds. But then it starts to accelerate. So it says that it accelerates at a constant rate of 1 meter per second for 3 seconds. So after 1 second, it's got 1 meter per second quicker. So we'll be here. If you look at the axes, the graph again, I've got a dot where we'll get to. And then after another second, it'll be another meter per second quicker. So it'll be here, and then the same thing after another second, so it's here. And that's all the information we're given. So we draw a line through these dots, and that is our graph. So we've answered the first part of the question. Then it says to calculate the total distance traveled. Now to do this, we need to use a key fact, and that fact is that the distance traveled is the area under the graph. So don't worry too much about why this is the case. Often you don't necessarily need to know why, and it won't be looked at in too much detail. You could look at it, you could go and read about why, but often for the purposes of your studies, and certainly for the purpose of this video, we're just going to take this as a fact that you need to remember. So the distance traveled is the area under the graph. So if you have a velocity time graph with a curve on it, and you can calculate the area underneath that curve, that's the distance the object traveled, the object that is being represented on the velocity time graph. So we just have to calculate the area underneath this curve. So that means the area between the curve and the t-axis. So it's this area here. I'm going to draw a dotted line just to show the enclosed area I need to calculate. Now to calculate this directly would be a bit difficult because it's a bit of a funny shape. But if I split it into 2 smaller shapes, it's a lot easier. So I have done that here with this dotted line. I've got a rectangle and then half of a square. So if you look at this top part of this triangle, it's a right angle triangle that is half of a square with sides 3 and 3. So we just need to calculate this area, all the areas of the 2 shapes, add them up, and we get the distance traveled. So let's try that. So we say that the rectangle, well, it's got one side length 6, and what's the length of the other side? It's 5. So that's just using the axes on my graph. So I can say that the distance traveled, S, is equal to 6 times 5 plus the area of the top triangle. Well, that has side length 3 and 3, as I said, so if we times 3 by 3, we'll get the area of this square here, but we only want half that area, so we divide by 2, so we get plus 3 times 3 divided by 2. This is equal to 30 plus 9 divided by 2, which is 34.5, and that's in meters because it is a distance. So that is how you can use a velocity time graph to find the total distance travelled by a moving object.